Alright guys, cheers for coming everyone. Now I'd like you to all welcome Professor Moriarty from the University of Nottingham, and he's going to talk about mechanical atom manipulation.
Thank you very much. Great pleasure to be in Lancaster. It's remarkably, I think, though my memory fails me, as I was saying to Rich earlier on, I think it's the first time that I've been in the topmost ranked department in the UK, which is shockingly lax of me. So I think the title that I gave Rich, and the answer I gave Rich, had a rather more grandiose title involving matter compilers, etc. You might think, well, what's a matter compiler? Well, just a quick show of hands. Are many of you familiar with the name Eric Drexler? Just a show of hands. Wow. Okay. So some people, many along the west coast of the US in particular, would feel that Drexler can lay claim to being the godfather, the forefather of nanotechnology. So he has been a particularly big name in some circles with regard to nanotechnology. And many of you, well, maybe some more of you might be familiar with the sort of whole grey goo concept, that we're going to, nanobots and nanoassemblers are going to take over the world and we're going to be knee deep in self-replicating nanobots. That was Drexler. That came from Drexler. And a lot of his ideas are science fiction, and he's been widely castigated by the nanoscience community right across the board. But to give the man his due, back in the early 80s, he was telling us, and being criticised roundly for saying so, that it would be possible to do reactions on an atom-by-atom basis using mechanical force alone, and moreover, to make that computer-driven. And so the idea then, and that he does, as I say, he deserves kudos for that, because that's perhaps not routine in labs now, but certainly there are many groups around the world that are working on that particular type of problem. Let's let this thing cycle through one more time. Actually, no, let's get rid of that bit at the end, which is one of the more embarrassing aspects of it. This is pure science fiction at the moment, but like the best science fiction, it makes you think, or should make you think. Arthur C. Clarke, Asimov, Douglas Adams, etc. They all make you think at some level, and so the idea here is that when you have some technology that looks like about the same dimensions as a microwave oven, and inside that you have atom manipulation technology. As we're going to see, it's going to zoom into what's actually in the guts of this. And the idea is that you take in very basic molecules, you break those down into component atoms, and you build that up into another structure. So ultimately, some of the proponents of this idea believe that we're not too far away from a technology where you have something that looks like a microwave, you go outside, you pick up some grass, you throw it in this thing that looks like a microwave, you press a button, and ding, 30 seconds later out pops a steak. Because the only difference between grass and a steak is how you rearrange the atoms. And we laugh at that and we smile at that, and many of us would say, well, it's a technology that already exists to do that. It's called a cow. And that's another interesting aspect of nanotechnology, and much do we try to beat biology and much do we borrow from biology. But, you know, I find these ideas intriguing, and certainly this is what's driving a lot of the research, this type of atom-by-atom manipulation, building up structures to a predefined blueprint is really what's driving a lot of what we're doing in Nottingham and what a large number of groups around the world are doing. But you can see that basically you've got tips, which are transferring atoms from tip to tip, molecules in this case from tip to tip, breaking those down and then using those to build up various structures. And you can see it looks very much like macroscopic technology scaled all the way down. And the question, some of you may be skeptical, and I hope many of you are skeptical, many of us actually doing this are skeptical, but the question is, well, how would we set up something like that? Where would the energy source be? What sort of precision can we get on our ability to manipulate matter? What are the fundamental limits of controlling the placement of atoms and molecules? And that's really what I'm going to focus on, faltering steps towards control, not just at the atomic limit, but the term that's increasingly being used, turning into a bit of a buzzword in the scanning probe community, is the subatomic level. And I don't mean at the quark level, I mean at the resolution better than atoms. So we're talking about being able to resolve single bonds or the effects due to single bonds, and to exploit matter and manipulate matter at the level of single bonds. So, I know I've got an undergraduate audience here, so I'm going to make this quite a gentle introduction to nanotechnology. In particular, What I'll be talking about are scanning probe microscopes in detail. You can see that the title of the talk is Mechanical Atom Manipulation. There's another aspect of this which is very, very important, which will take up the last 20 minutes or so. And it's the trouble with tips. So the way we can see individual atoms, see in inverted commas, and manipulate them is using a technology which, well, it's a microscope because it allows us to see them in the atomic scale, but it's a microscope like no other. It's not based on optics. There are no mirrors, there are no lenses. Instead, you have something which is, I heard you having an interesting discussion about the optics module you're taking at the moment. So for scanning probe microscopes, we don't have to, we have no optics. Instead, we take a tip, preferably sharper than this, we bring it in close to a surface until we get some sort of interaction. Now, in the earliest type of scanning probe microscope, that interaction was a tunnel current. It was a flow of electrons, a quantum mechanical flow of electrons due to the tunneling effect between the tip and the sample. You move it back and forth and you measure how that interaction changes. And at each pixel, as it were, you build up, you use that interaction to map out the surface. I'm going to talk pretty well exclusively about something called non-contact atomic force microscopy, or better still, dynamic force microscopy. Here, the interaction we're ultimately interested in is the chemical bond that forms between the atom on the end of the tip and the surface. And, you know, this is what we sort of envisage our tips to look like. In reality, our tips look nothing like this. And that's going to be, as I said, towards the end, that's what we're really going to focus on. Because I think you'd be quite disturbed by the level of abuse that scanning probe microscopists give to the tips. To get atomic resolution, we will do a range of things, including applying a voltage pulse between the tip and the sample. That doesn't work after a while, going to very high currents to try and arrange the atoms at the end. If that doesn't work, we smack the tip into the surface. If that doesn't work, we smack the tip into the surface, drag it across the surface, push it in a little bit further and take it out. The level of abuse, and it's not just us, pretty well every group does this. They might admit to it, but they do. And then once you get the tip into a state where you've got atomic resolution, then you can do nice things. So you can try and put molecules on the end of it, and I'll show you how we do that. But at the initial stages of getting that tip to give atomic resolution can be pretty abusive. So that's the general area of non-contact AFM. I'll spend a little bit of time talking about that. This mechanochemistry term actually stems from Drexler, and it's doing chemistry with purely mechanical forces. And there's been a lot of work using scanning tunneling microscopes to inject electrons and form bonds that way. But the problem is, once you inject those electrons, they scatter. You lose, in many cases, quite a degree of precision. Sometimes you have a very high degree of precision, but in many cases, particularly on silicon surfaces, you inject electrons, those electrons travel across the surface, they get injected into surface states, and then they have some particular scattering length, etc. And you can have reactions occurring very far away from the tip. If you really want to get down to the limit of single atom precision, the best way to do it is in terms of atomic force microscopy. So the simplest possible mechanical or electromechanical or chemomechanical device you can think of is a switch. And if you think about, there isn't a traditional switch in here. If you think about a traditional toggle switch, it's bistable. You've got one stable position there and another stable position there. The question is, can you scale that all the way down? So you've got two atoms basically, a structure like this, or a state like this, and a state like this. And can you flip that back and forth at the atomic level? And well, I wouldn't have it up there unless we could do it, so I'll tell you about that. As I mentioned, the key thing here, and this is something, again, another guilty secret of the scanning probe microscopy community, slightly less guilty, but because we all recognize this, but sometimes we forget about it, is that any probe image is a convolution of the tip state and the surface state. The tip state is just as important in forming an image as the surface. And so it's very important to try and get a handle on just what the tip is doing. And so I'll tell you about work we've done recently where we pick up molecules on the end of, pick up a molecule on the end of the tip, and then use the surface to image the tip. The whole process is you can invert it. So basically what you hope for is you've got a sharp tip which images objects with a larger radius of curvature on the surface. So you've got a big molecule like this and a tip like this, and you image it. You can, of course, turn that on its head. If you have structures at the surface which are sharper than your tip, then you can use the surface to image the tip. And what could be sharper than a molecule? Well, you have to think about the type of electron orbitals and the spatial extent of the orbitals at the surface. If If you have narrow orbitals, or orbitals with a narrow spatial extent, you can exploit those to image the tip. That is not only important in terms of imaging, but is extremely important when it comes to manipulating. Because there are some tips that you can do manipulation events with, other tips you can't. And ultimately what we're pushing towards is not that far removed from those grandiose Drexler ideas right at the start in our videos. Can we automate this process? At the moment, scanning probe microscopy involves students, postdocs, or even sometimes members of staff going in the lab and spending 12, 15 hours, a couple of days, in the worst cases maybe a week, getting the tip into, not only to give atomic resolution, but to give a particular type of atomic resolution. The computer is just as capable, and in fact more capable than us because it doesn't get tired, of recognizing when it's got a good image. How can we teach the software to recognize when it's got a good image, and how can we take that person who's spending his time literally doing something which, if you had a reasonably intelligent chimpanzee, you could teach them to do. And I've sat in the lab doing it myself. You're sitting there just pulsing the tip, trying to press it, and it's a very laborious trial and error process. Can we automate that? So I have to click the button, but remember I don't have USB. So, those who actually did the work, I put this at the top right at the start rather than at the end, because I usually run out of time. So this is not just the group that I supervise. We have the nanoscience group in Nottingham, 5 members of staff, 8 postdocs now at the moment. It's something like 25 PhD students. Though if EPS or C keep going at the rate they're going, that will plummet pretty soon. So the people who were important for the work I'm going to describe. Adam Sweetman in particular, who's currently in Japan on a JSPS fellowship, has driven this work, the non-contact AFM work in silicon I'll discuss. Rosanna's writing for a PhD now, Subashi's another postdoc. Sam at the back here is also very important. Sam is a balance of experimental theory, all the density functional theory work I'll describe, all the theoretical calculations are due to Sam, and Christine over here is responsible for the C60 on tip work. We also collaborate very closely with Lev Kantorovic's group in King's College. And these two people, this is Rich Woolley and Julian Sterling, who have been driving the automated optimization of probes work. In a nutshell, scanning probe microscopy in a nutshell. You have a sharp tip, you stick it on a piezoelectric crystal. The great thing about piezoelectric crystals, many of you will have come across these, those clicky things you use to light your gas. You apply, you stress your piezoelectric crystal and it generates a large voltage, you get a spark. Turn that idea on its head, apply a voltage to a piezoelectric crystal and you cause a distortion. And you can use that to control the tip. With good voltage, with good high voltage amplifiers and with good crystals, you can get down to the picometer level pretty routinely now in terms of control of the tip. So to put that in context, hundreds of the diameter of an atom. And then you move it back and forth across the surface, as I said, measuring an interaction. Now, we're going to look at not just atomic force microscopy, but dynamic force microscopy. With atomic force microscopy, as opposed to STM, the advantage is that you don't need to have a conducting surface or conducting tip. What you do is you have a cantilever, sorry I'm using this as a prop a little too often, with a tip sticking at the end. In standard contact mode atomic force microscopy, you bring that in, touch the surface, you have a repulsive interaction between the tip and the surface, and you move it back and forth. You have a laser shining off the back of the cantilever, you look at the deflection of the laser, and from that you work out what the force on the tip is, and you thus build up a map of the surface. Problem with that, of course, is that in many cases taking a sharp tip, putting it on the surface and dragging it across does neither your tip nor your sample any good. So shortly after the AFM was invented, maybe 4 or 5 years later, and I think this is a really elegant exploitation of first-year vibrations and waves physics, whereby you take your cantilever and instead of operating it in a static mode, you pull it back from the surface. Of course, if you pull it back from the surface, you lose sensitivity. The way you regain sensitivity is to oscillate the tip at its resonant frequency. And by oscillating the tip at its resonant frequency, when we move it in and it starts to interact, just as if you've got a mass on the end of a spring, you change the mass, 1 over 0 root k over m, you get a different interaction and therefore you shift the resonant frequency. Gravity obviously plays absolutely no role in our experiments other than to keep the kit on the ground. So you move it in and you see if it's an attractive interaction, the resonant frequency will shift downwards. If it's a repulsive interaction, it will shift up. And we can map that shift in resonant frequency down at the millihertz level. So we have a great deal of sensitivity to the change in resonant frequency and therefore to changes in force of the surface. So, as I said, the first type of structure, or the first type of rudimentary device you think about is perhaps a switch. Even before you go anywhere, think of a transistor or diode characteristics. So let's get something which is bistable and you can flip back and forth. And actually all the way back, this is not particularly new in terms of scanning probes. It's pretty new in terms of atomic force. In terms of scanning probes, all the way back in 1991, Don Iger's group, many of you will be familiar with the IBM logo and the quantum corral where they formed basically patterns of atoms on the surface and use those to confine electron waves and set up standing waves and eigenstates within those wells. Really staggering work. So Don Iger's group was the first not only to manipulate atoms but also the first to demonstrate an atomic switch. This is quite some time ago. So you've got an atom, in this case a xenon atom, on a surface. You locate your tip above it and you apply a voltage pulse and therefore a current pulse. And you can take the atom off the surface, put it on the tip or put it back again. Importantly, the mechanism here is that you inject those electrons vibrationally excite that atom, and that causes it to basically heat up. It's vibrational heating, and it dissolves from the surface and ends up on the tip. And then, quite a number of years after that, because it's not a simple experiment to do, it was shown that you could do it for molecules. This is a simple biphenyl molecule, so basically just two benzene rings coupled together. And depending on where you inject electrons, you can get this thing to flip in different ways. You can also use larger molecules, and you can try and manipulate using the tip of the microscope. That works pretty well. Or you can try intramolecular manipulation, whereby you flip the positions of atoms within a molecule. Obviously, this is a bistable system, and each time you're flicking it between two stable positions. But more importantly, each time the mechanism here is an injection of current. None of this thus far has been done with pure chemical force. And that was the first question when it's only recently we got into relatively recently, it was 2008, we got into this atomic force microscopy game. And one of the things we wanted to know is whether you can use chemical force alone to do this type of switching. And that brings us all the way back to Drexler. And shortly after we started on this, there were a couple of groups that did some really staggering experiment. This is, again, over here we've got IBM Zurich, where they've measured IBM Zurich was where the STM and the AFM were invented. And they've pushed a single atom across the surface, and they've mapped out the potential energy landscape for that atom as it moves across the surface. That's the experimental data, that's not theory. In many ways, it's quite remarkable. The experimental data looks cleaner than the theoretical data, and also took much less time to run and derive. So, as well as this work, which was back in 2008, shortly after that, this is really elegant work from Oscar Kustance's group at NIMS in Japan, where they've taken basically an alloy of silicon and tin. So there's a mixture of silicon and tin atoms at the surface, and they've used the tip to exchange. So here you've largely got tin atoms, and then they've changed those here to form silicon, and here, similarly, they've replaced those atoms with tin atoms. So I don't want to bore you with lots of the details, but just quickly, how does non-contact AFM work? Well, it involves using frequency modulation techniques. So we're oscillating the sensor, the tip on the end of this, it moves back and forth at its resonant frequency, and then we use a phase lock loop to lock in, make sure that we're locking in so that the response of the cantilever is 90 degrees out of phase with the driving force, which, as you know, means that you're on resonance. So that's one aspect of this, and we control, or we monitor, we measure the resonant frequency, or the shift in the resonant frequency, more correctly, the shift in the resonant frequency when we're up here compared to when we're down here. That's one thing you have to do. The other thing you have to do is you have to keep the amplitude constant. So you also have an amplitude control loop, which is what this thing is doing. And then you also have to have the feedback loop that is in every scanning probe microscope, whereby as you're moving the tip back and forth across the surface, you can operate in what's called a constant height mode, where you just hold the height constant. But the problem is then if you run into some contamination or you run into some structure on the surface, you crash your tip in, and that tip, if you've spent days possibly preparing, you lose it. So instead you have a feedback loop which measures that interaction, and for example, let's consider the scanning tunneling microscope. If it finds that the current is getting greater because there's something on the surface, it pulls the tip away, maintains a constant current. And so that allows you to continue to image the surface without doing damage to your tip. And what it looks like in the lab, well, before I discuss that, we use a slightly different sensor than is conventional. These are becoming more prevalent, but conventionally these type of sensors aren't used that much in non-contact AFM. They are used quite a lot in Lancaster for a completely different measurement. What we have here is a quartz tuning fork, just like the tuning fork you have as the timing element in any quartz watch or quartz clock. You take it out of the can and you stick a tip on the end of it. The great thing about quartz is that it's very, very stiff compared to the traditional silicon cantilevers that are used. And so that means you can get very, very close to the surface with a very small oscillation amplitude without the tip being what's called jumping to contact. What can happen with soft cantilevers like silicon is that because they're so soft, when you bring them into the surface, I mean the spring constant is low, when you bring them into the surface and you try to oscillate them above the surface, what can happen is that the interaction with the surface can exceed the stiffness of the cantilever, and it can jump in to contact, which is exactly what you don't want. So the great thing about tuning forks, because they're so stiff, you can have a very low oscillation amplitude. Why is a low oscillation amplitude important? A low oscillation amplitude is important because you want to have a sensitivity to atomic forces, and those forces tend to have a length scale of an angstrom, a couple of angstroms, something like that. So you really want to be oscillating your tip in and out of that potential on that type of length scale. And there are a whole wide range of other useful aspects of this. Quartz itself is piezoelectric, which means we don't have to use an optical measurement, we don't have to bounce a laser off the back. And that's what the kit looks like. The business end is over here, the microscopes back here. This is a commercial setup from a company, a German company called Omicron, who really are sort of world leaders, market leaders in provision of ultra-high vacuum SPM kit. And this is, I'd love to say this is a typical image, it's not, it's one of our best images. And each blob here is an individual atom on a silicon 100, so I'll explain what that means. Have you done, for the undergraduates, have you done solid state physics yet? Have you done any solid state physics? So they haven't come across Miller indices. Okay, I'll explain very quickly what that is in a second. So, gets us all the way down to 5K. It's a tuning fork with a tungsten tip attached. Forget about that. Again, a link back to perhaps what you've done in vibrations and waves. Certainly, Rich mentioned that he's going to be honoured of taking over a Fourier transform course, and one thing that I think is really elegant, if you want to measure the resonance curve for something, you can do it laboriously by changing the resonant frequency, changing the driving frequency, and looking at how the response varies. Or you can hit it with an impulse, which if you look at that in frequency space is a wide range of different frequencies, and then you can use a wonderful technique called Fourier transform to give you the resonance curve, which is what we do. And from that we can measure the Q, and we can measure all the parameters of the tuning fork. Right, so this is the core experiment I want to introduce you to first of all. So what we're trying to do is miniaturize that down. Now, silicon 100, all that means, the 100, just to orient the undergraduates here, you think of a silicon crystal, you think of a cube, as you've got a basic repeating unit, which is a cube. That 100 tells you basically which face or which plane in that cube you're looking at. So you can think of it as Cartesian, well, you can think of it, it is Cartesian axis X, Y, and Z. and they define a vector. And so in this case we've got 1, 0, 0, which means we've got this vector pointing along, say, in the x direction, and we're talking about the planes of the lattice, which are normal to that. So it just defines a particular type of plane in the crystal. And luckily for silicon 100 does some quite neat things. If you just could imagine cutting through the crystal and nothing else happening, then what you'd end up with is that, where each atom at the surface, you see it forms a square lattice, and each atom is back bonded to 2 underneath, and then it's left with 2 dangling bonds. Silicon forms 4 bonds. We call them dangling bonds. They're not connected to another atom. And that's not a particularly healthy state for the system to be in. It's got quite a high free energy. So what it does